individually. Okay, so let's say you wanted to sort of like try to understand, let's just see if we can understand the flow of why this is true. So we take the matrix and we suppose that its number has m rows and n columns, and we fix domain and codomain spaces v and w of dimension n and m. So by fix, that means choose, because if we're given a matrix, it's going to be a matrix for a map between any vector space V, domain V, and codomain W, because it can act on those vectors. Okay, and we assume that we have the bases B and D, B for the domain and D for the codomain. Then H represents some linear map with respect to those bases, and here's the range space is given by this, okay? The range space of H equals all the H of V's for every V in V, okay? So we take so for every vector in V, we have an H of V. Well, we can take the V and expand it in a basis B, right? So that H of C1 beta 1 up to Cn beta n for any C1 to Cn, because the basis of V, which is B, the betas cover the whole space. They're a basis for the space. But then we can use the fact that H is linear to write this as H of C1, H of beta 1, Cn of H of beta 1. Okay, so the range space here is the span of the H of beta 1, H of beta 2, the images of the basis vectors. So the rank of H is the dimension of this space. So we have the rank of the map. Now we have to sort of say, what's the rank of the matrix? So we have a representation of the rank of the map. So the rank of the matrix is the dimension of its column space, right? Which is the same as the rank of its row space, but the rank of the matrix is the dimension of its column space, which is the span of the set of columns, but it's the span of these things. So I'm taking the column space of H, which is the rank, is the span of, because the matrix H is defined to be these H's in the domain basis, okay? To see that the two spans have the same dimension, so we have two representations of the range space and the column space of the matrix, but we can see we've got them down in terms of the same vectors, okay? Okay, so we can't recall that. But what it says is the spaces with the same dimension are isomorphic, right? So if we could make, what we want to do is we want to show these spaces are isomorphic. If they're isomorphic, they have the same dimension, okay? So once we fix the basis D of W, there's an isomorphism from W. We want to sort of, we can, how am I going to motivate this? Well, let's go on and say that what we're going to do is we're going to end up with, we go through, we construct a map to see from here, we take H of beta 1 and take it to H of beta I, right? We take each of these, like H of beta 1 goes to H of beta 1 in basis D, H of beta N goes to H of beta 1 in basis D. Now we want to show that this is, that it's linear and that it's, we have to show that it's an isomorphism, because there's a linear relationship between the members of the range space if and only if the same. Okay, well it's going to go through and it's going to show that that this map is the vectors are linearly independent and they span the space, so they're going to form a basis. And there's going to be the same number of them. So we're showing that the H of beta D's, we know that they're going to be linearly independent. So that, in other words, that this is linearly independent if and only the D's are linearly independent. And so what what's going to happen is you can see essentially because of the way that we've defined the space here, we have a natural isomorphism between the bases of the range space and the column space of H. I know this isn't, I've sort of left out details here because I don't want to go through all the details and try to make it plausible, but there's sort of like something here that you've defined the matrix in such a way that it correlates with the range space. So you can see that the rank, we can sort of then accept that the rank of a matrix is the rank of a map. And if you read through this, and we can go through it more carefully if you wish, but I just wanted to sort of go over that a little bit. I'm not sure how useful that was, but that's